Yes, sir, visible.
Okay. Let me start with this quote by Mark Weiser, who was actually a technologist, chief technologist at Xerox. He is considered to be the father of ubiquitous computing. The most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it. Like how right now our mobile phones have become. The zip for our dress has become, or even the innovation of a button has become. So these are some things which actually we have even forgotten who might have come up with that innovative idea, but it has brought in a profound change, and it has become like in our everyday life we are making use of it. So this would be the outline of today's talk, that is Introduction to Internet of Things, which actually happens to be the base class or else base parent class for both industrial Internet of Things as well as social Internet of Things. So after IoT, we will discuss about industrial Internet of Things and social Internet of Things. So what is Internet of Things? As many of you would have already gone through, studied, or even experienced, it is something which devices can connect to the internet. If you would look at the evolution of communication, initially we used to communicate with letters or through signals in terms of smoke or light. This happened in 1800s. Then came the telephony network, which was in around 1880s, which actually was based upon analog communication, which ruled the world for almost 50 years. It was able to actually provide you with end-to-end resource reservation, because of which quality of service was able to be supported, and you were able to make voice transmission. Then around 1940s came the TCP/IP protocol, or else the data networks. Even though it came into existence, it could never give the or guarantee the QoS requirements of how the circuit switching or the telephony networks provided until 1980s. In 1980s, the data networks was able to match the speed of a or a QoS requirements of a circuit switching network. In 1900s, slowly data networks started to overshadow the circuit switching network. In 2000s, actually, circuit switching network do not exist anymore. Even your mobile phone, let it be any kind of communication, now is being done over data network itself. Even your telephone or mobile phone communications are using digital with LTE, long-term evolution. So this has been a slow transition up to 1990s. By 2000, mobility was a very 90s to 2000, mobility came into picture, mobile communications developed, where things are started to move around. Once that got matured, Internet of Things came into picture, where communication has matured to a certain extent. Can I make things to communicate with one another? That is what is Internet of Things. Physical devices that are connected to the internet to share information or collect information. This is the history of IoT or Internet of Things. Mark Wieser's paper on ubiquitous computing, basically, they did not coin the term Internet of Things, but the abstract idea of what Internet of Things will provide was spoken with different terminologies. There was a Coke vending machine that was placed in Carnegie Mellon University. People would walk onto it to even check whether there is beverage available or not. Later, it was automated such that there would be a small web page which would actually update whether there is beverage available or not. The people would check that and then decide upon visiting the machine to collect beverage or not to go. This was the first instance of IoT being put into use. There has been a lot of research topics. Kevin Ashton basically presented the Internet of Things as a use case to Procter & Gamble in the year 1999. This is the year that the term Internet of Things was coined. There have been many other terms like Internet of Everything coined by Cisco. Which will look as we go further. These are some of the dimensional work that has happened. See, initially the networks did not comprehend or visualize mobility as part of their functionality. That is the reason TCP/IP stack that was designed doesn't support mobility as so well, which was designed in 1945. Around 2000s, mobility became a big thing, and also the number of devices that would be connected to the internet was not visualized. When all this came into picture, IPv6 came into picture. That is why you have anytime connection, whether it is day, night. This was provided even with PCs or personal communication devices. Any place connection could also be achieved with laptops or PDAs that were connected on the go. Once these things matured, people started to look at anything connection. How to connect things to the internet so that we are able to get or tap upon the information and also try managing and controlling the devices remotely. These are some of the IoT enabling technologies. If you go through different papers, you would, in some way or the other, you would still see these terminologies or the layers being talked about in the IoT world. One is the sensor technologies, which actually tries to sense the environment. It acts as a nervous system, collects details, and any smart device that we say must be able to have sensing. It must be able to communicate, that is communication. It should have some kind of an antenna by which some technology by which it is able to send and receive data, at least send. Third is processing, a minimal amount of processing it is supposed to support. So once the sensors or sensor technologies collect these data, it can be in terms of RFID, radio frequency identifier, or else energy harvesting sensors. Once they collect the data, they will actually use the wireless communication and networking part of the system to send out the information. All the information that are collected can either be stored onto a edge device like your gateway, or else it can be uploaded onto the cloud. Once it goes onto the cloud, you will be doing analytics or try to make out information from the data collected. And from that information, you will actually send signals onto the actuator to perform specific tasks. This is a very generic view of how it works. This is another example of how an IoT system works. You have a IoT device or a sensor which collects data, collates the data, and transfers it onto the IoT hub or IoT gateway. In order to transfer, it needs to actually use the antenna or else the transmission subsystem. Any sensor subsystem will consist of sensing subsystem, communication subsystem, and processing subsystem. That is the reason they have actually tried to differentiate these three things here. Together, they will actually be doing a data collection, which after doing it, it will communicate the collected data onto a hub or a gateway. The gateway will either process it if it is a small amount of processing, or else it will actually communicate it onto the cloud. All that data that it is collecting, it will communicate onto the cloud. The data that actually is sent onto the cloud, you do an analytics on it, make learnings out of it, store that information onto your system.
Sir, your voice is not audible, sir. Unmute your mic, sir.
Yeah, this actually, now is it audible?
Yes, sir. Yes, sir.
Okay. Basically, IoT lifecycle consists of collection of data through sensing, and it communicates the data onto the gateway, or else from via a gateway onto the cloud. Then analysis of the data is done to come up with information, and based upon that information, an action is taken. So devices and sensors help in the collection of data. These devices can be in at home, or else in car, or else industries. Once the data is collected, this data would be communicated. It might use different technologies. in the communication front, like let it be Zigbee, let it be IRDA, let it be Bluetooth, low energy, let it be IEEE 802.11ah, Zigbee. These are all some of the communication protocols that are used. Analysis is about actually being able to make information out of the data that is collected. This is actually the architecture of IoT. You have the application layer, which will have a user interface, and application layer can be built for specific applications such as transportation, healthcare, agriculture, supply chain, and others. Gateway and network layer basically is the layer which helps in the communication to happen. It gives you with a network infrastructure which is supposed to be robust enough to handle the amount of data and also guarantee quality of service. The amount of time taken for the data to reach should be in bounds. It should not be indeterminate. Management service layer basically deals with data analytics and also security and privacy. As I discussed even in the previous slide, sensor layer is actually the digital nervous system, which is actually the lowest abstraction layer in the IoT architecture. As we discussed, basically, these are some of the standards that are used in the IoT world. IPv6 or low power wireless personal area network, 6 low pan. The IPv6 or the traditional conventional networks that we have designed doesn't support for resource constrained or energy constrained devices. PCs or mobile phones that we connect are devices which have high energy level, whereas IoT deals with several hundreds of nodes, each of them being able to have a very limited amount of power. So energy becomes a very constraining factor or challenge in IoT. So all the processes, let it be in terms of network layer functionality, let it be in terms of data link layer functionality, it is supposed to take energy as a critical parameter in designing it. So low power wireless personal area network 6 low pan is actually an open standard that has been defined and proposed by Internet Engineering Task Force, IETF. Zigbee is one protocol that was actually that was pretty successful up to 2015-16, which was able to operate at a much lower energy level. But of late with Bluetooth LE and also IEEE 802.11ah coming into competition with Zigbee, it's having a tough time in terms of practical expectation and survival. Light OS basically is a Unix-like operating system which is designed for wireless sensor networks. It serves to build smart device development. It gives us with a platform to do that. One M2M basically is a service layer that helps us in embedding the software and hardware into the connected devices. Data distribution service, DDS, that was developed by Object Management Group. It is a IoT standard for real-time, scalable and high-performance M2M communication. When we talk of middleware protocols, Advanced Message Queuing Protocol AMQP, which is based on subscribe publish model, is a standard protocol that uses TCP, and I think it is proposed by IBM. Constrained Application Protocol COAP is another middle layer framework that has been designed by Internet Engineering Task Force, which is able to support low power compute constrained devices. It operates on UDP and it's able to provide quality of service. These are some of the frameworks that are used in the IoT world. Amazon Web Services, AWS IoT, basically it's a cloud computing platform for IoT. Even ARM microcontrollers that is developed by ARM, they have come up with a ARM Embed IoT platform, which is able to facilitate connecting sensors and gathering data with a predefined framework. Microsoft Azure IoT Suite is another platform that consists of services that enables users to interact with and receive data from their IoT devices. These are all some of the frameworks which specialize on specific services. Like if it is cloud services, AWS IoT is better. When you are dealing with sensors, then actually ARM embed microcontrollers, microprocessors, sensors you wish to connect, then actually this platform is better. If you are dealing with subscribe services and application layer deployment, Microsoft Azure IoT Suite is considered to be better. Calvin is another open source IoT platform released by Ericsson, which helps in building and managing IoT applications. Google also has a platform called as Brillo or Weave, which helps in deployment and implementation of IoT applications. If you look at why are we looking at Internet of Things, why do we wish to connect the machines or systems onto the network? One is the decline in the cost of compute. With the advances in semiconductor industry, we are able to see a drastic drop in the cost to performance metric. That is basically performance to cost metric. for microprocessors, microcontrollers, let it be even storage and networks. Cost has very drastically come down. The performance of operations of devices have drastically gone up in the past 10 to 15 years, which has inspired or made IoT a viable or imaginable solution. General Electric coined the term industrial internet. Cisco termed it as Internet of Everything, and some of them call it as Industry 4.0. These are all some of the terms that, as we discussed before with Ashton coining Internet of Things, these are also synonyms to the same IoT. When we talk of Industrial Internet of Things, IIoT, basically it deals with application of IoT for specific disciplines, but the discipline is very vast. It consists of energy production, manufacturing, agriculture, healthcare, retail, transportation, logistics, aviation. We would be discussing some of the case studies in some of these disciplines to look at how IIoT is being envisaged, or how it is being seen, or how it is evolving with time. Basically, industrial internet or IIoT tries to provide you with better visibility and insight into the company's operations and assets through integration of sensors, middleware, software, and backend cloud compute and storage systems. Basically, together we call it as automation. Why is IIoT seen as a very game changer in the in the industry or in the global economy? The power of 1%. If with IoT I am able to save or optimize or make my operation efficient by just 1%, I would be able to make a savings in aviation industry up to $30 billion. Similarly, if I am able to just make a saving or efficient operation of just 1% in the oil and gas industry, I am able to make a savings of about 66 billion. The same applies with with oil and gas, it's around 90 billion. Fuel savings from the gas-fired generators in a power station gives you around 66 billion. So these are actually the key reasons or economic backbone because of which IIoT is seen as a game changer. There is a lot of technological promise and also economic viability. If someone is able to build a solution to this, they would be able to tap into a very big trillion dollar economy. So these are actually the key opportunities and benefits based upon the same order. Everyone look for IoT to help in increased profit as the first priority, then increase revenue flows, and then lower the operational expenditure or operational cost. what are some of these are the advantages of IoT. Some of the challenges to implement IoT is adequately skilled and trained staff. And since IoT is a new concept and it would keep evolving with even in terms of days, months, you must be able to adapt and change. So commitment to innovation. The more critical challenge with IoT is security. In one of the casinos that had implemented Internet of Things, it had an aquarium which had a thermostat which would record the temperature and accordingly raise the temperature or reduce the temperature. Basically, it was a IoT solution for the aquarium. But unfortunately, they had stored the data onto the same database, which was connected to store the customer information. Through that thermostat, someone was able to actually tap into the sensitive customer information, and it created a huge flaw in the security system. These kind of occurrences or solutions that has a issue tries to actually give it a challenge for implementation. The other one is interoperability. With so many varied technologies, with so many varied players, even though there is an attempt for standardization, interoperability or interoperation of these devices is a challenge. It's not so easy to accomplish it. These are all some of the challenges for bringing in IoT. Some very interesting case studies when we talk about in remote submersible remote operational vehicles, that is trying to survey the surface in an ocean or in a sea. They used to send vehicles which was connected via a physical cable onto a mothership, and through that mothership, signal or supply of power and control signals were sent on to the remote operational vehicles. This is the way actually it operated. But with Internet of Things coming into picture, this umbilical cord or else the physical cord that connects to the mothership has ceased. It doesn't exist anymore. Even the power, some amount of battery power is stored, and the devices are made efficient such that it's able to generate power from either thermally or else through the waves that are generated in the ocean or sea. These are all some of groundbreaking applications that have been seen. With the advancements in cloud computing that we say, even truck tires. Nowadays, you buy tires, you replace it, and you don't use it, which actually would cause loss to the uh, owner of the trucks. Now a new model has come in where he is able to actually install the tires, the number of miles that he drives, and also the wear and tear for the tire is sensed by the sensor, and this information is sent on to the owner of the owner of the tire. The owner bills, the company bills the truck owner according to the usage or a wear and tear for that tire. It is based upon the concept of cloud computing, pay as you use. Okay, these are all some. How is this possible? It is because it's able to have a sensor which is able to estimate or approximate the wear and tear of the tire and communicate that onto the company, who are able to appropriately charge or bill the customer. Robots are also seen as one of the use cases for Internet of Things, which would be sensing, processing, and acting, or would be replacing the human labor. This Rolls-Royce Total Care, basically the aircraft engines that we say, nowadays aircrafts are not bought, but the engines are subscribed. There is a concept of Rolls-Royce Total Care, which basically means you can actually subscribe to the Total Care of Rolls-Royce. They will do the maintenance of the engine. You will be paying on to only for the services. But they have installed hundreds of sensors in the engine such that they are able to actually, without opening things and physically examining, they are able to still track the operation and detect possibility of repair or flaws only by using sensors. And also, interestingly, Rolls-Royce has been able to build a virtual engine, digital, which we call as a digital twin for the physical engine. By using all these sensors, they have been able to capture all the different parameters, and with that parameter build a virtual engine. If they wish to try out something, they actually do it upon the virtual engine. This model has been able to save a lot of money and also innovate by trying out things on the virtual world instead of really building onto a engine to try out some new concepts, new platform or new device being brought in. The same way, actually, even in oil and natural gas, if you would visit ONGC and all, ONGC has a huge amount of data, even to decide upon whether they have to dig somewhere, to decide on whether there is a chance of getting oil, is a science in itself, and a lot of data is being analyzed so that we don't spend a lot of money in digging and end up with a dry well. So IIoT is being used and seen as a very hot and viable option in the oil and natural gas industry, which can reduce cost and increase the efficiency and also safety. Some of the use cases of IoT in healthcare is now in Europe there is a concept called as healthcare kit that comes, which is able to have a thermometer or else and sugar level monitor, SPO energy, your oxygen monitor. Then you have a BP monitor. All these are digitally connected or can be connected to your smartphone, which actually collects all this data and sends it on to the cloud, or even you can have your own gateway or end system which actually keeps monitoring until everything is normal. If there is any abnormality, the complete data that it has fetched will send it onto a nurse or else a visiting your physician. The physician would go through it and either recommend certain things or else take appropriate steps. So by this, neither the patient needs to travel and visit a physician very regularly, but at the same time, optimally, continuously, we are able to still monitor the uh, different parameters. In Scotland, basically, there is a robot called as Giraffe, which was built in 2013, which helps to monitor and support family members who are suffering from dementia or old age. A giraffe is able to have a video screen by which a family member is able to make a Skype call and talk to that other person, or else even have a camera using which you are able to constantly monitor and make the other person feel safer and at care. There is also another healthcare robot called as the Baymax, which is actually has a soft synthetic skin, which helps in detecting the medical conditions, and also it has sensors on their paw as well as on the soft synthetic skin is sensitive enough by which it is able to monitor the child's psychological well-being and also other parameters and keeps updating to the parents. IoT being used in a smart office, the amount of energy that is being utilized in office can be optimized to up to 40% if we are able to leverage the functionality of IoT into this. Buildings are also considered to be one of the primary reasons for which greenhouse gas emission happens. When we talk of inventory systems, that is supply chain management, where a lot of things are being shipped and we wish to track so that we don't miss out on something. This RFID tags and RFID readers give us as a solution which is cost effective and much faster and automated. We are able to now track the movement of the inventory and make it more optimal. With sensors on temperature and humidity, the environment where the goods are being stored can be constantly monitored. Certain grains or else edible, degradable substances can be optimally managed in the if we are able to sense and take appropriate steps. As you would know, Caterpillar basically is a company which works upon earth moving equipments and many other mechanical equipments. They have come up with a solution to image monitoring solution. There is a infrared camera that is placed above the driver's seat, such that it's able to constantly monitor the eyes of the driver, and looking at the blink rate and the pupil size, it's able to predict whether the driver is falling asleep. As a precautionary step, one is it blows an alarm so that the driver becomes alert, and also there is an option to shake or vibrate the seats of the driver. These are all some things which actually has already been put to use. There is also something called as a reed switch, which senses the presence of a magnetic field. When the magnetic field is very near, then actually it closes the connection. This reed switch helps in digital switches, which has to be enabled and disabled at a much faster rate. These reed switches are basically used in pill cameras, defibrillators, glucose monitoring devices, and nerve stimulation devices. So for most of these applications, these reed switches are being used. Even the cyber physical systems that we talk of can be seen as a synonym of what actually IoT can do. It's actually an integration of computation, networking, and physical processes. When we look at how IoT has evolved, how is it supported technically in terms of communication? These are some of the standards that has helped in the evolution of IoT or maturity of it. One is Wi-Fi IEEE 802.11b, which actually guaranteed a speed of around 2 Mbps, evolved onto 802.11n with a realistic bitrate of around 70 to 90 Mbps, but theoretically it promises around 300 Mbps. Then you have IEEE 802.11 AC and AD, which is able to have a data rate of about 800 Mbps and 6 Gbps, which uses orthogonal frequency multiple access, frequency division, multiple access, and multiple input and multiple output MIMO technologies as the critical technological things that has been able to improve upon the data rate. IEEE 802.11ah, as I discussed even initially, it's basically designed for neighbor area network, NAN, which is able to support low power use and long range, and it is a competitor for Zigbee or Bluetooth low energy, BLE. These are all some of the other predominant, prevalent standards or technologies that are used for wireless communication. With cloud computing, bring your own device, bring your own cloud, software as a service, and cloud services. These actually have been able to propel the advancements and the application of IoT, which actually is pretty challenging, and also it is trying to IoT basically has a very diverse needs in terms of electronic requirement, in terms of sensor requirement, in terms of analytical requirement, in terms of actuator requirement, all this. With cloud computing or being able to have as a service, we are able to get all these varied, diverse requirements so that we are able to build in a solution. So these are all aspects which we'll be going deeper into with each session as we go further. Let it be the networking session, let it be the cloud session, all this with sessions we'll be going deeper into each of it. Now, to just give you a brief introduction upon the social Internet of Things. In 1999, Internet of Things was coined. In the year, for every 10 years, there has been a newer generation of technology that has come in. Any technology has taken about 10 years for maturity. So Internet of Things, after having spent nearly 10 years, had matured, and with next visualization, social networks that we call as, which consists of this Facebook, Twitter, and other networking things, can we leverage the learning and the knowledge of social networking and try optimizing the Internet of Things? So this is the crust upon which social Internet of Things came up. Adzori et al. Basically proposed the social IoT in 2011. Which integrates social networking concepts into the Internet of Things. A large number of individuals tied in a social basically it is on a simple principle that a collective wisdom of many is always better than the wisdom of a single, even wiser person. This actually has been proved theoretically as well as by research. And based upon this, actually the social network which is able to have a huge collection of people, can the learning and wisdom of this be utilized for IoT? This actually is the crust. What are some of the advantages of applying social networking principles to the IoT? Basically, IoT is seen as a humongous collection of devices. The population of the Earth is around 7.6 billion. The number of devices that are connected are around or expected to be around 70 billion by 2030. So this amount of devices, if they are connected, navigability or managing the IoT network is not going to be easy. So in order to do that, the social networking that right now we are able to have a social network of people that is connected. How best is this management being done? Can the same be applied onto the IoT network? So that is what actually is SIoT structure can be shaped to guarantee network navigability. In social networking, we have a level of trustworthiness that helps us to leverage the degree of interaction among things that are friends. So the same kind of concept of trustworthiness can we apply it onto the Internet of Things. The models that are used to study the social networks, can we reuse it to optimize IoT functionality? There is a term called as homophily, basically, which means among your friends, whatever we will have similar taste or similar requirements of what our friends will have normally. So whatever they search, at least about 70 to 80%, our search would also be similar. So homophily basically is a scheme that is used to exploit the similarity in the interest of friends, to enhance the internet search or to optimize the peer-to-peer networks. If you would see, can I try optimizing the search by looking at who are my friends and what they have searched? That can actually help me to
मी बरेच दिवस झाले आता मी केलेली नाही, पाहायला लागेल त्याच्यामुळे मला.
could you please mute yourself? Could you please mute yourself? So basically, your search can be optimized, and also peer-to-peer networks helps you to share and
VHDL. Yes.
So peer-to-peer networks helps you to share files that are needed, or documents that are needed. When we have friends, obviously the files among the friends would be relatively common. So when I am able to identify friends, then obviously I am able to even optimize the functionality of the peer-to-peer network. Being able to build a social relationships even among the IoT I'm able to increase or improve the efficiency and effectiveness of security, because friends are basically a trusted circle. Similar to how Internet of Things we call things, in the social Internet of Things, SIoT, we call things as blobjects or objects that blog. This objective of SIoT is very important, and it is pretty crystal clear that to keep separate the two levels of people and things, to allow objects to have their own social networks, to allow humans to impose rules and to protect their privacy and only access the result of autonomous inter-object interactions occurring on the object social network. Basically, what he means to say is, if I am going to make the devices to have a to connect to SIoT, that doesn't mean that the owner or the human's personal information or privacy should be compromised. The device should have its own social network, and the owner or the human should have the control over the amount of personal information that is being shared and with whom. He must be able to control all this. When we talk of blog jets or objects in SIoT, we try to give in different relationships to objects. One is called as the parental object relationship, or POR, established among objects belonging to the same production batch. So the same company, the devices that are created by Samsung would fall under parental object relationship. Co-location object relationship, established among objects used always in the same place, like in the workplace, the objects that are all placed at one place, that forms a relationship called as a co-location object relationship. Co-work object relationship, in terms of colleagues or the places that you visit very frequently at workplace, the objects over there can have a co-work object relationship. Ownership object relationship basically means the objects who belong to one owner would form or come under this relationship. SOR, or social object relationship, established when objects come into contact sporadically or continuously because their owners come in touch with each other during their lives. So these are all some of the relationships which can be defined for objects. This actually is the social Internet of Things SIoT architecture, which consists of the entity layer, which is similar to how an IoT sensing and actuation layer is. You have component abstraction layer. This layer is distinct or unique for a SIoT. Then you have communication standards, protocols, technologies, and gateways, or communication layer, which again is a same as the IoT layer of communication or networking layer. Social objects for human social interaction layer is again a new layer, which is unique for social IoT. Application layer is again the same. So effectively, if you see, out of these 5 layers, there are 2 layers which are very distinct, social interaction layer and component abstraction layer when compared to IoT. So the entity communication and application layer functionality are similar to how the IoT reference architecture itself is. The other one is the component abstraction layer, which does important jobs like identity management, object profiling, ownership control, service discovery, trust management, relationship management, and all this. These are all the critical and important functionality in a SIoT, which is performed by the component abstraction layer. The other one is the social interaction layer, which is used as an interface, and it actually is a social agent that tries to establish social communication between smart objects and humans. So with this, I come to the end of the introduction aspect. These are all some of the research challenges in SIoT. One is heterogeneity or interoperability. Because of heterogeneity, it leads to interoperability challenges. Mobility and dynamicity. Object tracking. Application, basically service discovery and searching. Effective resource management. Security, trust, and privacy. These are all some of the hot research that is happening on the SIoT front. If you have any questions, you can please ask.
Dear participants, if you have any queries, kindly unmute your mic and you can ask, or use your chat box to ask your queries. Participants, any queries? Sir, there is a question in chat box. They're asking about Zigbee, sir.
Basically, there is a another session, madam, which is scheduled day after tomorrow on device-to-device communication. We will discuss in detail about Zigbee in that.
Okay, sir. Thank you. Participants,
Sir,
any queries?
Sir, can you please throw light on the chemical system, sir?
On the
Chemical industry where we can use IoT.
Sir, your question is not clear. So kindly repeat it, sir.
See, basically in any industry where you wish to see, in chemical industry, there are chemical gases that are generated. And also there are situations where human intervention would be more hazardous. So in those scenarios, if you are able to study the system to analyze, assess how automation can be brought into it by putting in sensors and being able to track. And the least it can do is actually give alarms or send messages onto a service personnel to check it. So these are some of the applications even in the chemical industry.
Thank you, sir. Thank you.
See, social IoT, when we say, it is just an extension of IoT devices. IoT devices will still be prevalent. Only thing is now actually if I am going to have a Samsung phone with me, and does it need to still get upgraded from the Samsung server, or if I have another phone which is going to be placed next to me, which is having a latest version of upgraded firmware, can I take it from there and upgrade it? These are things which can be done if I am able to have a social Internet of Things where a device is able to detect its parental object relationship with another object. If they are able to know that both belong to the same production, then they can actually upgrade or utilize the services of one another. If I have a digital personal digital assistant, PDA, and I have my family or I have a set of friends whose birthdays are already marked, then the PDA can automatically send birthday greetings to those family members or to acquaintances if I am able to give it the owner control. I am able to provide it with that control to that device. It will automatically do this. The same way, if I wish to buy something which someone else has bought it, I can actually my PDA can just track some other PDA who falls within my friend list and provide me with those information. So these are very simple but very effective applications which is seen or which is going to be part of everyday life. I hope I was able to answer your question. Security challenges in IoT, basically we will be dealing with security in the coming sessions. Just kindly go through each session. This is just the introduction aspect where I just wanted to highlight upon some of the applications. Just give you a feel of how IoT, IIoT or SIoT can bring in a change in terms of daily operations. Thank you all for attending this session. Again, there will be another session at around 10:30, 11:30, which you can attend, which will be on routing algorithms, I suppose.
SIoT and IIoT specific routing protocols and models.
Okay, madam. Kindly take over, madam. Thank you very much.
Thank you, sir. A good beginning makes a good ending. Your talk was particularly appropriate at this time to start with new initiatives in SIoT and IIoT. With your insightful presentation of these basics, I'm sure, sir, upcoming sessions will be easier to understand. Thank you once again, sir, for your neat and consistent presentation. Thank you, sir, for your valuable time.
Thank you.